Welcome to this lecture series in real analysis. Today we will be defining what is a Riemann integrable function and what is the Riemann integral, and let us recall some relevant things. So first we will use the fact that any continuous function on a closed interval is uniformly continuous. And here closed interval can be replaced by compact set. And what is uniform continuity? So a function is said to be uniformly continuous. So suppose f is a function defined on some closed interval. This is said to be uniformly continuous if for each epsilon greater than 0, there is some delta greater than 0 such that whenever two inputs to the function are delta close, the corresponding outputs are epsilon close. Okay, and then we will need, or at some point we will need Darbo's theorem, which says that if we have a bounded function on a closed interval a comma b, then you form the upper sum corresponding to some subdivision, and if we choose subdivisions whose norms become smaller and smaller, we will converge to the upper integral. So what was the norm of a subdivision? Norm of tau was the maximum of all these things. So I need to have more notation for this to make sense. But what is happening is tau is this subdivision, and the norm of tau is the maximum of the length of all the parts that are there in tau. So that's the norm of tau. The upper sum corresponding to tau is, recall, this is equal to notation is the greatest enemy here. So instead of Li sigma, I'll write ai minus 1. And what is this? This is the supremum of all the values that the function takes on the ith part. So let me not expand on that thing. So Darbo's theorem says, this is somewhat informal version of it. The formal statement of this same thing is that for each epsilon greater than 0, there is some delta greater than 0 such that whenever tau is a subdivision of the domain with the property that its norm is smaller than delta, then the upper sum corresponding to tau and the upper integral of the function, they are epsilon close. So that's what this very nice innocent looking statement means. Okay, and we will use our old friends. A continuous function on a closed interval will achieve its supremum and infimum somewhere. And here also closed interval can be replaced by any compact set in this statement. So roughly, I just wanted to highlight these things before we proceed, and now let's move on. So let's define the oscillation of a bounded function. So we have a bounded function, and we have fixed a subdivision of the domain. The oscillation of the function f with respect to the chosen subdivision is defined as, the notation is w, then put a subscript. This is equal to the difference in the upper sum and the lower sum. Okay, but let's see what that is exactly saying. So this is by definition equal to where of course sigma is a0, a1 up to an. So This is the supremum of f over the ith part. This is the infimum of f over the ith part. This is the length of the ith part. And I've just expanded this definition out. And when we were introducing this module, we were just beginning this module, we wrote this as omega I f sigma. So this, we recall, was written as omega I f sigma. Omega looks like little w. In fact, we perhaps could even have chosen little w for it. All of these notations are not standard. I'm pretty sure these will vary from one textbook to another. So we wrote this thing as omega I f sigma, and omega looks like small w, and this is, well, capital W looks like capital W. Okay, wonderful. So that's the definition of oscillation. And Darboux's theorem immediately says that the limit of the oscillations as you vary the subdivision, in fact vary so that the norms of the subdivisions go to 0, this limit exists and is equal to that. Again, this is an informal statement, because what does it even mean to say taking limit over some subdivisions? So what this means is, again, for each epsilon greater than 0, there is some delta greater than 0 such that whenever tau is a subdivision, tau satisfies the property that its norm is small, meaning less than delta, then this difference is at most epsilon. Very simple, immediate from Darboux's theorem. And this is just an exercise. So if you follow this, it will take just a little bit more time to prove this. So this I leave as an exercise. Very important to do these exercises. These are what make you digest the definitions. If you ignore these, you will always feel a little hazy, ambiguous about every little, you won't be getting the confidence. Okay. So now we can define Riemann integrability. I mean, we could have defined it in the beginning, but what is the definition? Fix a bounded function. We say it is Riemann integrable if, I think I've commented on this before. We say it's Riemann integrable if the upper integral agrees with the lower integral. We have previously shown that this is always true, but when this happens, we declare f to be Riemann integrable. And we had seen earlier that this function is not Riemann integrable. So here we have a function that is not a Riemann integrable. And the first one is Riemann integrable. So we have seen those things. In fact, we've also seen that the square function is also Riemann integrable. What we saw is that we computed the upper integrals, and I hinted that if you compute the lower integral, then you will get the same value. So this is Riemann integrable. And this we explicitly saw that the upper and the lower integrals disagree. The upper integral is 1 while the lower is 0. So once we have a Riemann integrable function, its Riemann integral is defined as either the upper or the lower, whichever, because they are equal. They are the same value, and we write it as simply this. So there is no under bar or over bar, just this much. All right. And just a point of notation, in many textbooks, in fact, many times it is convenient to write the symbol as that. What is not acceptable to me, at least, is writing something like this. If one writes something like this, that to me is meaningless. What is dx? Here, at least x is a dummy variable, but here it doesn't make any sense. Also, what doesn't make sense is this. If you just write this much, what is this? Anyway, all right, so let's move on. Now for a simple criterion for Riemann integrability, fix a bounded function, then the two things are equivalent. First is that f is Riemann integrable, and second is that for each epsilon greater than 0, there is a subdivision of the domain for which the oscillation of f is less than epsilon. So you can achieve arbitrarily small oscillations is the point. I mean, that is the criterion. These two things are equivalent. And the one-line proof of this is the exercise that I left you with, that the infimum overall subdivisions of this, sorry, what am I writing, is the difference of the upper and the lower integrals. This is, from this, you can immediately show the equivalence. So if f is Riemann integrable, then by definition this is 0, and hence this is 0, which means this is true, and conversely. But it is a very good thing to keep in mind. Okay? So now let's move on. So now the most important thing, we have defined something, we have defined what is a Riemann integrable function, or what is a Riemann integrable function. But how do you recognize if something is Riemann integrable? It's not very clear. If I give a concrete function, we should be able to decide. We should have some tools to decide if it is a Riemann integrable function, and some tools will be developed here. We will, by the end of this lecture, we'll have a very big class of functions, or sufficiently big class of functions, which we will have seen to be Riemann integrable. In the next lecture, we will increase that repertoire. So first and foremost, every bounded monotone function defined on a closed interval is Riemann integrable. And here, for example, I've drawn a monotonically increasing function. This is my best attempt. Okay. So let's prove it for this, or for an increasing function. The similar proof will go for a decreasing function. All right. So let us write down the upper integral, upper and lower integrals. Sorry, let us write down the upper and lower sums for a chosen subdivision. So let sigma be some subdivision. Sigma is a subdivision of the closed interval. And what is the upper sum? So then, just unraveling the definitions. I mean, we are not in this writing, we are not even exploiting the monotonicity of the function. So what is the upper sum? This thing, and here the supremum over the ith part, and then the length of the ith part of the subdivision. What is the lower sum? Infimum over the ith part, length of the ith part. But now, here is the point. What is this? Since our function is monotonically increasing, what is m1f? It is the supremum over this part. But since the function is increasing, it is simply f of a1. Right? Similarly, what is the supremum over the second part? It is simply f of a2. So that's very nice. So therefore, this expression is nothing but that thing. And what about the lower sum? That would be the following. Right? So we have that. But now we will invoke Darboux's theorem. So instead of sigma being some arbitrary subdivision, let us choose sigma so that when we take the difference, a lot of terms go away. So okay. So let sigma be the most simplest, or maybe I'll say, okay, so we may, how do I say this? To define delta as b minus a by n, and a0 is of course a1 is a0 plus delta, A2 is A0 plus 2 delta, and so on. So we can arrange that. We can choose this particular subdivision where these are equi-spaced. So in that case, all of these numbers are the same now. And once we take the difference, this will be, a lot of terms cancel out. Here we see f of a1, here we see f of a0, then we say f of a2, and here we see f of a1. So I hope you see that a lot of terms cancel out, and what remains once we take the difference? This is just f of an, ln, well, ln is what? Ln is delta. And here we'll have f of a0 minus f of a0 delta, right? This is now delta for each I. That's how the subdivision has been. Maybe I'll highlight it. Okay. So this of course goes down to 0. So this goes to 0 as n goes to infinity. Because f was the bounded function, so f(an) minus f0 is bounded by some number, and delta is becoming smaller and smaller as n grows larger. So this certainly goes to 0, and that's it. Therefore, f is Riemann integrable. Okay, so now for something a little bit more interesting. Fix a continuous function on the closed interval a comma b, then it is Riemann integrable. So, coarsely speaking, every continuous function is Riemann integrable. Note that by the continuity of the function on this and the closedness of the interval, we know that f is bounded. So it is legitimate to ask for the Riemann integrability of f. Okay. So we will use the criterion for integration or integrability, that fix an epsilon greater than 0. By the criterion for Riemann integrability, we want to show that we want to show that there exists a subdivision sigma of the closed interval a comma b such that the oscillation corresponding to sigma is less than epsilon. So this is what we want to do. And the kind of sigma that we will build, the most convenient one, would be the one where we have equal parts. All parts have equal lengths. So choose an n, and we will decide how large that little n needs to be. So let little n greater than equal to 1 be such that something, I think I would need more space later. So let me pull this figure down maybe. Yeah, so that should be fine. Great. Yeah, so this we will fill up later and define delta n as this ratio, which is the length of each part that our subdivision will have. So what is our subdivision? Sigma n is our subdivision, and that is defined as a0 is equal to a, then a0 plus delta n, a0 plus 2 delta n, and so on up to an. So needless to say, a0 is a, and this is of course b. So that's our subdivision. And now, what is the difference between the upper and the lower sums? By definition, it is this expression, right? That's what it is. And now here is where continuity of the function kicks in. So first of all, continuity of the function implies uniform continuity, and that will imply that this can be uniformly made small. This expression can be uniformly made small, meaning for each I, meaning if delta n is small enough, each of these will be small enough. So what am I saying? So since f is uniformly continuous, we know there is a delta such that whenever we pick two things in the domain, which are delta close, we get the images are epsilon close. So epsilon positive was already fixed, and for that epsilon there is a delta such that this happens. So that's immediate by the uniform continuity of the function. Any continuous function on a closed interval is uniformly continuous. So we have that, and now if this delta n is smaller than delta, little delta, if this is smaller than little delta, then this will be at most epsilon, right? What is this? This is the supremum of all the values that the function takes on the ith part. This is the infimum of all the values that the function takes on the ith part. But if you pick 2 points in the ith part, you pick any 2 points in the ith part, take the f value and take the difference of the f values, that is less than epsilon. That's by choice of little n. So let me fill the blanks. So n greater than equal to 1 be such that delta n, if defined this way, is less than little delta. Little delta is here. That little delta comes from epsilon and the uniform continuity of the function. Once the value of little delta is known to us, we define little n so that this happens. And now once we pick any 2 points in the ith part or any part, you pick 2 points in any part, the difference in the f values will be less than epsilon in the absolute value. If this is x, this is y, fx minus fy in the absolute value is less than epsilon, immediate from here. And hence, this difference is at most epsilon. So this is at most epsilon delta n. But because of the summation, this is epsilon times b minus a. If you sum up delta n times, you get b minus a. So the upper sum minus the lower sum is less than equal to this quantity, but epsilon was arbitrary. So yeah, I mean, just to fix this small scuffle, I'll write epsilon by b minus a here. I can easily write it. I'll just exploit the uniform continuity again, and instead of writing epsilon, I can write this. And here, instead of writing epsilon, now I can write epsilon upon b minus a. It's just a cosmetic difference from the previous one. And therefore, I get epsilon upon b minus a times b minus a, which is epsilon. Wonderful. Wonderful. So this difference is less than epsilon, and that is what we wanted to show. So I hope the idea was clear. It was just an application of uniform continuity, right? If you choose 2 points in one common part, provided the part has small length, the oscillation in that part, this is the oscillation in the ith part, will be small. That's what uniform continuity tells us. That's it. Very simple. Now here is a generalization of the previous proposition. So what do we have? We have a Riemann integrable function to begin with. And suppose, well, since it is a Riemann integrable function, it is assumed to be bounded. And suppose its image is contained in this closed interval. And we have a continuous function defined on that closed interval. So one can compose phi and f. And let us call G as the composite of them. We claim that G is Riemann integrable. So the composition of a Riemann integrable function with a continuous function is again Riemann integrable. And this is an immediate generalization of the previous proposition, because if you take f as the identity map, then what is this composition? This composition is just phi. Right? Now, identity map is Riemann integrable. That is very easy to prove, as we already did, even in the previous lecture, I think. So the identity map is Riemann integrable, and therefore this shows that any continuous map is Riemann integrable, which was precisely the previous proposition. Okay, so let's see. It's not a hard thing or anything. In fact, I encourage you to pause the video and think of a proof yourself. That is the best way to understand this proof. I don't know how well I will be able to present and expose this. Anyway, so let's try. So first of all, let us say t is a positive real such that this is at most t. So what do I mean by this? Well, since phi is a continuous function on a closed interval, it is a bounded function in particular, and t is a uniform bound on absolute value of phi. So what this means is that phi of x in the absolute value is at most t for all x in the domain of phi. So that's what I mean by that statement. So pick a t with this property, and to follow the proof, you may assume that t is 1. That's the best way to follow the proof. Okay, and we will of course use the criterion for Riemann integrability, which is that suppose we choose an epsilon greater than 0. We want to show that there is a subdivision sigma of the domain of the composite that we are interested in, such that the oscillation, let me write a g, the oscillation of g corresponding to this subdivision is less than epsilon. So this is of course wg sigma. This is what we want to do. Okay. And now I want to leave a lot of space and then fill that space later. And maybe I'll need an extra page for that. So let me try doing it this way. So what do we, I mean, what are the kinds of terms that will appear when we will consider this guy? So suppose sigma is this subdivision. For now, it's just some arbitrary subdivision. So I'm leaving a lot of space here, which I want to fill later. So sigma is this subdivision, let's say. What is this oscillation? This is equal to, by definition, this thing. So again, this is the supremum of g over the ith part. This is the infimum of g over the ith part of sigma, times the length of the ith part. That's what it is, but let's even further unravel it. So the supremum over the ith part, this thing, times gx, of gx minus infimum. Right, that's what it is. And gx is phi of fx, so I'll write that. Okay, and we want to bound it. We want to choose a suitable sigma so that this whole thing is less than epsilon. Right, so we would like to say that these things are small. So small that when you sum them up against these lengths, you get a small number. So that would have been very easy if we knew that over the ith part, fx doesn't oscillate too much. If over the ith part, the oscillation of f is small, then this whole quantity, the oscillation of the composite, is also small. Because phi is a uniformly continuous function. Phi is a continuous function on a compact set, and hence uniformly continuous. So if we knew that this doesn't oscillate much over the ith part, then we could bound it in principle, roughly speaking, right? So we need to choose a sigma. We need to choose a sigma suitably, but we do not have a direct control over the oscillations of f. We only know a global property about f, the fact that it is Riemann integrable. That's all we know. So we have to exploit that, or we have to locate our suitable subdivision by exploiting that global property of f. And so that's what we now turn to do. Okay. So we will of course use two things. We will use the uniform continuity of phi and the Riemann integrability of f. All right. So first let's nail down the uniform continuity part. So fix a, we have already fixed an epsilon greater than 0. We already have that here. So by uniform continuity of phi, we can find a delta such that whenever x and y are in the domain of phi and they are distance less than delta apart, we have their images under phi are less than some small number apart, and by back calculation that number I have chosen to be this much. Right? This thing at the bottom is has come about in retrospect, and I might even need to change it later. But the point is, on top there is an epsilon, and it is multiplied with some absolute number. These numbers are fixed. Epsilon is something that is what matters here. Okay, so we have exploited the uniform continuity, and now this suitable sigma will come about by exploiting the Riemann integrability of the function f. So choose a sigma by the fact that f is Riemann integrable. We know there is some subdivision sigma of the domain of f such that the oscillation of f corresponding to this subdivision is small, such that this is, well, again, back calculations, this I have written to be delta epsilon by 4 times t. So why this precise number? So that at the end I get something less than epsilon rather than something less than epsilon times some constant. There's nothing wrong with it, but it's just better this way. Okay. So all we know is that the oscillation of f over sigma is small. That doesn't allow us to control this for every I, right? Just because the oscillation is small, that doesn't mean the function is the function over every part oscillates a little. This is a global thing, right? This is what wf of sigma is the ith oscillation of f times the length of ith part, and then you sum it up, right? Where what is the omega if? Omega if is the oscillation of f over the ith part. It is, by that I mean, it is the difference of the supremum of f over the ith part and the infimum of f over the ith part, right? So what we know is that some sort of an average of this is small, but that doesn't mean that for every I, omega if is small. So this is where we'll need to kind of be a little bit more careful, or have a more careful analysis. So pick those which are showing small oscillation over, pick those parts over which f oscillates a little. So here is what I want to say. So first of all, sigma is, we'll write sigma as a0, a1 up to an. So this will go away. So that's how we notate sigma, and let G for good consider only those i's such that for these i's this is small. This is, so what have I written? This is small. So this is the difference of the supremum of f over the ith part of sigma and the infimum of f over the ith part of sigma, right? As we just said. So those are the indexes of the good parts, and the bad parts are those which are not good. So B is the complement. Okay. And now what do we know? We know, by the choice of sigma, we have that the sum is less than delta epsilon by 4t. That thing. We have that. So what do we get? We get that the bad parts. So this implies, therefore, if we just sum up over the bad parts, summation I running over bad parts, this is in particular small. The same bound, of course. You just dropped some terms to obtain that. Okay. But by definition of badness, this is dominated by, this dominates something. What does it dominate? Since I is running over bad parts, this is at least delta for each I over the bad parts, right? The good parts is where this is less than delta. So the bad parts is where this is at least delta. So this is at least I and B delta Li sigma, right? And therefore, we conclude that this length of the bad part, if you just take the length of the bad parts and sum them up, that is less than epsilon upon 4t. So what this says is that the total number of bad parts, or the total length of the bad parts, is not much. And therefore, in this estimate, we can disregard the bad parts. Not that we will disregard it carelessly, but in terms of the higher level ideas, we are kind of now in the position to drop the bad parts and only care about the good parts. Okay, so this sum will be partitioned into two regions. So here I should write a now. So this sum will be partitioned into the good and the bad. Run I over the good parts. And the same thing, supremum and the bad part. So let's first deal with this. So this is at most. So the first thing will be coming up verbatim. And the second thing, let's bound that. So what is a bound over this thing? A simplest bound is 2t. Because mod phi was at most t. And therefore, a very simple bound over this is twice of t. So this is less than equal to summation over the bad twice of t times Li sigma. But what are we doing? We can just take this 2t outside. Oops, what did I do? Just taken the 2t outside. And we know a bound on this. This is at most epsilon by 4t. So this is less than equal to, again the first part is verbatim. What am I doing? Plus epsilon by 2. Because this is now bounded by epsilon by 2. This much was at most or less than epsilon by 4t. So this whole thing is less than epsilon by 2. This is why I chose 4 times t in the denominator there. Or maybe not there, but here. Okay, so we have that. And what about bounding this? Well, we are running over only the good parts. So on the good parts, fx, the oscillation of fx is not much. The oscillation of fx is at most delta, right? So if you pick two things in the good part, suppose this is the good part, this is ai minus 1, this is ai, and I is good. So whenever you pick something here, 2 points, the difference, let's call this x and that y, fx and fy, they don't differ much. They will be less than delta apart. And hence, phi of this minus phi of that will be less than what? Epsilon by 2 times b minus a apart. So since we are running over the good parts, we can estimate this also. So this is less than equal to epsilon by twice of b minus a Li sigma plus epsilon by 2. And here again, this we can just pull out, right? And this is at most b minus a. The length of the good parts is at most b minus a. So this is less than equal to. I mean, here we could have written a strict less than, so I am good. I can write a strict less than. Sorry, here I wanted to write a b minus a and then an epsilon by 2, which is epsilon. So we are done. We have indeed shown that this is less than epsilon. Yeah, so a little bit more complicated than our usual proof, but not that bad. I mean, once you realize that you can break this into good parts and bad parts and then approximate the good and the bad separately, it's not such a bad proof. It's not such a difficult proof, but a very interesting result. So as a consequence, just give me 1 second. As a consequence, we now know that if f is Riemann integrable, then so is the absolute value function coming from f, right? Because the absolute value function is a continuous function. So this is fine. And something like this also. If f is Riemann integrable and takes only non-negative values, then the square root function of f is well defined. And this is also Riemann integrable. Something that is not immediately obvious from the kinds of things that we have done, but now that we have this theorem in our hand, we have a very nice, such thing. So you can increase this list at your own will, at your own time. And now let us proceed. So this is the last thing that I want to discuss. It's a beautiful result. It's a generalization of one of the things that we just saw. So we saw earlier that if f is a continuous function, then it is Riemann integrable. Of course, continuous function defined on a closed interval. So if this were a continuous function, then it is Riemann integrable. It is not much of a leap to think if suppose f is a function which has only one point of discontinuity, then it is also Riemann integrable, not much of a problem. You can prove it similarly. Or even finitely many points of discontinuity, not a big deal. But what we are trying to say is that suppose f is a bounded function with the set of discontinuities, so D is the set of those points where f is discontinuous. And if this is a countable set, we are not even assuming finiteness, we are allowing for countability of it. Even then, f is Riemann integrable. So if f has only countably many discontinuities, f is Riemann integrable. So there is so much freedom when it comes to Riemann integrability. In fact, even this can be further generalized, but I don't think we'll be getting into that in this lecture series. Maybe I'll change my mind later, but as of now, no. This is already pretty good. So how do we prove such a thing? It's not very difficult, but it has interesting ideas in it. So here I won't be giving full details, but I hope I'll be able to explain the main idea. So first of all, suppose we choose a bound for the function f, right? Since f is a bounded function, we can find a positive t such that the absolute value of f of x is at most t for each input. And best to assume t is equal to 1 to follow the proof. And we enumerate the countable set D. D is the set of all the points where f is discontinuous, but since it is given to be countable, we can enumerate it. right? Fine, so we enumerate that, and here is the point. If this were the empty set, then we know that we are done, because then f would be a continuous function, and we already know that continuous functions are Riemann integrable. We mainly exploit the uniform continuity of the function f. So if this is a countable set, the main idea is the following. The main idea is to trap this in a small part of the domain. This is where the function behaves badly. Trap it in a small part, and that small part, since it is small, when we consider the oscillation of the function f, that small part will not contribute much to the oscillation. And the good parts we kind of know how to do, because we'll have kind of uniform continuity of the function on that part. So essentially that is the idea. In fact, with that idea, you should try to write the proof yourself. But maybe this trapping this in a small part, I'll explain a little bit. And then I don't know at which point I will leave the details. Okay, so fix an epsilon greater than 0. And we want to show that the oscillation of the function f with respect to sigma is less than epsilon. I mean, we want to show that there is a sigma. We want to show that there is a sigma such that, so there is a subdivision sigma of the domain of f such that this happens. This is what we want to do as usual, the criterion for Riemann integrability. All right. So, okay. Yeah. So let O be those points which are good in some sense. O is those points for which there is a neighborhood u of x such that the function doesn't oscillate much in that part, in the neighborhood u. How much? Well, we allow for the tolerance of this much, which of course is a result of a back calculation. So that's the set O. This is kind of the collection of good parts of the function where the oscillation is small. This is the kind of point which we like. And clearly each continuity point is here. Every point of continuity, O contains all points where f is continuous. Make sure you follow this. Pause the video and think about it if it isn't immediately clear. It might also contain points where f is discontinuous. That can surely happen. But it will always, or it will certainly contain all points where f is continuous. So therefore, the domain of the function is the union of the points in O and the points in D. And that is fine. And now I want to talk about the trapping of this bad region in a small part. So here is the thing. Define for each natural number k, dk as this interval. So it's an interval of width something, again result of a back calculation, this much. So this is an interval of width twice of this around the point dk, right? So here is the thing. If we sum up the lengths of these intervals, or even, since we haven't seen infinite series yet, we will see them later. I can't just sum up the lengths of all of them, even though you might have read something about that in your high school. The point is, these are all open sets, and together they, along with the set O, cover the entire domain. Why is that? Because together these dk's cover D, they contain the set D, and therefore, since this is the union of these two things, here I cannot write an equal to sign, I'll have to write a containment, right? Because these open intervals may fall out or come out of this thing. So I could intersect this with a comma b, but then that is another mess that I will get myself into. It's just a technical thing. So this thing is contained in these open sets, and therefore by compactness of this guy, there is a natural number n such that this is contained in this union. Fine. Now what is the length or the sum of the length of each di's that is here? What is the length of d1? The length of d1 is twice of this. What is the length of d2? Again, twice of this. Sorry, so here not twice. Yeah, twice. Okay, sorry. So what is the length of d1? You put k is equal to 1 and then twice of that. d2, you put k is equal to 2 and twice of that. So the sum of the length, maybe I have an extra page here. Yeah, okay, fine. So I have it. So the length of dk is twice of 2 to the k for t. Yeah, that's what it is, which is epsilon by 2 to the k 2 times t. And therefore, if we sum up the lengths from 1 up to n. So what do I mean by length? The length is the right end point minus the left end point, naturally. So this is equal to summation k from 1 to capital N, epsilon by 2 to the k twice of t, which is epsilon by 2t. Oh, this summation, which is formula for the geometric series. It is this thing. So I'm sure you've read that this is equal to that in high school at some point. Even if you haven't, you can just do a quick Google or think about it yourself or use induction or something. We have that, which is less than epsilon by 2t. Yeah. So the bad parts, the d1 up to dk's, they together fit inside something whose total length is very small. And the good parts we know how to deal with. So here is where I will leave the proof. I will not write any more details because they get cumbersome. It's better to fill them up yourself. Try your best. If you are unable to, you can just do a quick Google. Set a function with countably many discontinuities is Riemann integrable. You'll immediately get to a right web page. So fine, I hope I was able to explain the idea. And now I just want to give a quick application. So we have this very nice function called Thomae's function. So it is defined in the following way. F of x is first of all 0 if x is an irrational, and 1 upon q if x is rational and x is p by q in lowest terms. So what do I mean? So this function takes the value 0 if you have an irrational input. And if you have a rational input, first you express that in the form of p by q, where p and q don't have any common factors. So they have GCD1. Every rational number can be written that way. P and q are positive integers. Since x is a positive rational, p by q, where p and q are both positive or non-negative, p can be 0, and if x is 0, then p is 0 and q is 1. So you express x that way, and then you just throw away p and write 1 by q as your answer. So that's the function f. This is Thomae's function, and here is the point. This is an exercise. Show that f is continuous at each irrational. So it is possibly discontinuous only at rationals. In fact, I think it will be discontinuous at every rational. It will be. So the points of discontinuities of f is precisely the irrationals. The points of discontinuities of f are precisely the rationals and hence countable. And hence this is Riemann integrable. Such a messed up function is also Riemann integrable. But it is. So that's very nice. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.